All right. So there's not too many people here, but that's kind of what I expected, because this is the one class where I said nobody, and it's rainy. But I did say this is one of those classes where you don't necessarily have to be here for what we're going to talk about today. But I think you'll get something out of it regardless if you aren't planning on taking Comp 40 next semester. If you are taking Comp 40 next semester, that's what we're going to talk about today. I'm going to kind of go over what I think would be a good idea for you to know before you get into the class. And then we'll get into some details about the differences between C and C++. And then we'll go into a little more detail about some specific like hexadecimal things and some other things that you probably will want to know. Let me get the right piece of chalk here. Does anyone have any questions before we get going on logistics? We have finished up the labs. So we're done with labs. In fact, I put all the, good job getting through all the labs. I put all of the grades for labs on Trunk. So if you would, go into Trunk and make sure that I didn't miss a lab somewhere. Because what I did was, here's how I graded the labs. If you completed them and provided them and went to lab, then you got a perfect score. Like, that's really all I cared about, right? I mean, I wanted you to try and so forth and do well, but you got a perfect score on the lab if you like attempted it and were there. And you know how you have to sign in when you go there. A lot of times people forget to sign in, and if you don't sign in, I have no idea if you were there or not. I mean, I could go and check provide, but I'm kind of lazy. Like, I don't want to go and like check for all the people who don't sign in. So I might have missed your thing. If you were at all the labs and I gave you a 0, or if you were at a particular lab and I gave you a 0, just let me know, and I'll go check provide and make sure that the times will work out and all that, and then we'll be fine, and I'll change it. If you did miss labs, well, you missed a lab. It's not worth that much of your grade altogether, but they should be all set in there. And make sure you check the other grades too. So the only ones that we haven't put in yet, I haven't put homework 5 in yet, because there's still some people who are getting graded on those. I'll do that by the end of this week. And then the other one's 6 in the final exam, and that's it. So we're good. All right. Any other questions? Yes, Claire.
Just curious, for the final, are you going to allow to have
You can have another, you can have a 1-pager back in front, same as before. And the other question that kind of comes up about the final is that it is cumulative, but I would study the stuff that's since the mid-year, mostly. Like, if you want to go back and review linked lists and all that, that's fine, but do it after you've done your other studying. Make sense? Monday we'll have a good review session on what to expect. Okay, but it'll be very similar. There'll be some problems that you have to like explain. There'll be some problems you have to do a little bit of coding, not too much, but a little bit, and just stuff that's since the mid-year, mostly. All right. Okay. Any other questions before we get going? All right. I'm not upset if you decide you want to leave in the middle or whatever, because you're not going to be in Comp 40. All right? And some of you may know, in fact, a couple of you I know are very good at C already, and this will be like much review in that sense. Okay? Can you guys see that all right? It's tough to see that with the, hang on. Nope, that's not the right one. Nope. There. Is that a little better? Should be a little better. Okay. All right, so first things first, we're going to talk about what Comp 40 is all about. Right? All the like rumors you might have heard about Comp 40, most of them are true. And then we'll talk about the differences between C++ and C and what you should know going into Comp 40, or at least what you should kind of try to get familiar with before you get in there. Since particularly, like, there's no such thing as strings in C. They're actually character arrays. Right? So you've got these characters, they're just arrays, and they're terminated with a null character, and that's a string. There's no fancy like object associated with it. There's no cout statement. Like, everybody's used to going, oh, cout. There is no cout statement in C. Right? You have to use this other statement called printf. New doesn't exist. There's no new keyword. Right? You have to use this other thing called malloc, which stands for memory allocation. And you have to use that, and you also have to use free instead of delete. So things like that. And then we'll finally talk about some like hexadecimal, and we're going to delve into like the underlying program code and look at some memory in a program and say, hey, what are we actually looking at here? Because you're going to have to do a lot of that when you get into Comp40. Okay? All right, and then finally binary notation, which is like another thing that you're going to do a lot of in Comp40. Okay? So what's Comp40 all about? Well, what's the rumor about Comp40? What does the 40 stand for? 40 hours a week, right? Okay, is it really 40 hours a week? It could be. Some hours, some weeks might be. You know, the cool thing about 40 is that it is very hard to do really poorly in 40, right? What does that mean? It means if you don't do your assignments and you don't work, you'll get a bad grade, obviously. But if you do the assignments and you put in the time, you will probably end up doing just fine. Okay? Some things about 40 are a little like, you know, they're kind of harsh. For instance, if they ask you to meet some specification and they do a test, and Provide really doesn't do much testing as far as I know, but if they do a test when they're grading it and your program seg faults, they just give you a 0 for the assignment, right? Because they're like, well, you should have tested that. Sorry, seg faulting's not allowed, right? So it's, you know, it's a little harsh in that sense, but you will get used to doing lots of tests. You know, there's a reason I yell at you all about creating your own tests, right? It's so that you get used to doing it for classes like this. But in general, here's what they say on the course webpage, on the Comp40 course webpage, okay? You're going to end up going from introductory programming, which is what you're doing now, and even song search is kind of on the edge, right? I mean, the design document for song search, I mean, I made you do a design document, but it wasn't too intense. And you go from like that level of programming to the next level, where you've got real design documents, you've got more kind of professional programming under your belt by the time you get out of Comp40. Okay? The nice thing, I mean, one thing about Comp40, I've been talking to a lot of people who are either in it now or finished it last semester. Nobody said they did. They were upset that they took it, right? While you're in Comp40, it's hard and there's a lot of work, but it's kind of one of those courses where it's a trial by fire sort of thing, and you will get through it. Like there were some people, I will not name any names, but there were a couple students from Comp15 last semester who went into 40, and I was like a little worried about them, right? But they've done fine. You know, in the end, they've done just fine. So, you know, which is good. But what you're going to do is you're going to study the structure of modern computers. In other words, you're going to dig down into the details of how do computers work at a much lower level. Okay, like the architecture of it. I mean, it's the reason it's called a computer architecture class, right? You're going to talk about computer hardware. You're going to talk a little bit about operating systems, compilers, like how do the actual runtime runs your program. All those things, you're going to talk about how they work together to make your program either faster or slower. Okay, so that's kind of the big overview of what Comp40 is all about. And you will get more of this as you go in. But you're going to write a lot of low-level code, right? And some of you guys will smile at that because it's awesome. Some of you guys will go, oh, this is like hard. Well, it's a little bit of both. It's awesome and hard, right? You're going to write a lot of low-level code. And you're going to write that in C, not in C++, because C is actually a little bit what we call closer to the metal. It's more lower level than C++ even. Okay? You're also going to write some assembly code. Do you guys remember one day in here I showed you some assembly code? It was when we were talking about the first day of asymptotic analysis. And I threw it up there and I said, this will make your eyes bleed. Right? Well, your eyes are going to have to bleed a little in Comp40, right? Because you'll have to look at a lot of machine assembly language. What's really neat about assembly language is that you get into it and you realize there's not that much to it. Like there's a fixed number of things you can do with it. Now these days there's a lot more instructions than, you know, there's hundreds, but the ones you will need to know is like this many, very small amount. And they don't do much. Like that's the whole point of a machine instruction. It doesn't do much, so there's not that much to understand, right? It's hard to make things, like it's hard to make a big program with assembly code because they only do little tiny things, right? It's like, anybody do Legos at all? My nephews are all into Legos now. And I don't like Legos these days because you get a whole package and it's like all the pieces for like one thing are in Legos. It used to be you got a box of Legos and you made whatever you thought of out of it, right? They had like one guy and it was whatever you wanted it to be, right? Now there's special everything. But anyway, assembly language is kind of like having like a whole bunch of like 1 and 2 blocks and trying to make something from it, right? Like you can do it. You can make the Death Star from 1 and 2 inch like blocks, but it's hard, right? It helps when you have like pieces that are bigger, which is what the other code allows you to do. Okay? Here's the cool thing about Comp40. All of your programming projects will be done with partners. okay, which means that you have to like work with somebody else sitting in front of a computer like coding together. That's cool for a number of reasons, I think. Number one, you get to like have two minds working on one like problem, right? And that's like, how many times have you sat there and scratched your head and go, I have no idea how to do this, I better go to Piazza, right? Because I have no idea, right? You can talk to somebody about that. It's also nice because you have strengths and other people have strengths, and those strengths hopefully add together, right? And any deficits you have, hopefully your partner will have strengths in that. So that's nice. The other big thing is you're kind of forced to be accountable, right? Like it's not just, you can't wait until the night before to start your problem, your programming assignment, which some of you guys do. And you can't do that anymore because your partner will be like, look, we've got to get this done. And you would never be able to finish it anyway. But point is, you tend to start things a little earlier, right? And you just crank away, and you have somebody else who keeps you honest in that sense. So I think that's great. I've thought about trying to do that for 15, and we may do some of that in the next couple semesters. But doing programming partners is kind of neat. I mean, you get a grade for both of you guys, right? You do have to do design documents that are pretty in-depth. And you have to do a lot of reading because there's a lot of material to know, right? But I'm going to point you to some of the documents that you can go to up front. Okay? All right. You do have to go from C++ to C. Now, I know some of you guys came from C into C++, right? But you have to go, those of you who took Comp 11, and by the way, class is being taught by Professor Sheldon. So if you had him for Comp 11, then you'll have him again for Comp 40. And he made some comment about, I forget what it was. He said the interface was exactly the same in Comp 40 as it is in 40, whatever that means. I don't know exactly what that meant, but I'll have to ask him. But you go into this C language, right? Now, C++ and C. C++ builds on C, which is nice because you already know most of the stuff you need to know for C. But there are some tricky little things. Now, here's a little history. I've told you this history before, for the most part. But in the late 60s, early 70s, this guy named Dennis Ritchie, designed this language C, and he made it so that it would work on lots of different Unix systems and other computing platforms, and he made it for one real purpose, right? The purpose was so that he could make portable code that you could write it once, and it would run on this machine, and then you take it over to this machine, and it would run on this machine. And all you had to do was have a C compiler that would do that, and it didn't matter if the underlying machine was completely different, the code would hopefully run on both machines. And that's more or less true. It doesn't work all the time, but it's more or less true. The language itself is, as I said, close to metal. It's not a really high-level language, right? Compared to Python or Ruby or some of these other high-level languages, C and C++ is a little lower level, right? Which, to your credit, you guys have actually learned a fairly low-level language, all things considered. C++ is still fairly low level. Whereas if you went to MIT down the street, right, they only learn Python there. Like everything's in Python, right? It's rare that you ever get into C in classes there. So it's odd, you know? So in that sense, you're ahead of the game in that sense. Okay? All right. What is this C language? Well, happens to be one of the most widely used programming languages. This diagram here comes from, I still don't know how to pronounce this, Tiobe or Tiobe. There's a company that kind of tracks this stuff. Why? I'm not sure why they do it, but they track what programming languages are being used. They do it by doing Google searches and trying to figure out who's talking about what language. But if you look, C is the top language up here, right? It's the top one. The next one is Java. Amazingly, the next one is Objective-C. But where do we use Objective-C? Anybody know? Which apps? iOS apps. For your iPad or iPad or iPhone, you use Objective-C. And it's amazing because before 2008, nobody knew about Objective-C. Like barely anybody used it. And then the iOS came along and everybody used it, right? It was on Macs as well, but not too much. C++ is number 4. This one has been as high as number 1, I think, but maybe 2. But I think it's been as high as number 1. But it's kind of dropping, right? Which means that maybe in a couple of semesters we should stop teaching C++ in 15 and 11. You know, I don't know what the other choice is, right? Should we go to Python, right? Maybe we should. Python has kind of gone up and down a little bit, right? Can we go to some other languages? We're not going to go to Visual Basic, right? I can tell you that right now. We're not going to. Yeah, Max. We may go to C. Yeah, we may end up going to C. It just means that some things will be a little bit harder, right? Like you're not going to get some of the benefits of using strings straight out of the box. You got to know a little bit of that. But you're right. It will prepare you even better for 40. It's just a little lower level, right? You don't get classes. There's no constructors or destructors. So maybe it's a good thing. You never know. But maybe it's a good thing. Yeah. Sure.
Why not Visual Basic?
Well, Basic itself is not a particularly good language. I think a lot of people agree with it. It's just not it's not a great language. You know, there's a lot of better languages out there. But anyway, JavaScript, if you take any web design, you'll have to learn JavaScript, which also is very C-like in general, right? It's funny that the C-like language, C has such a large reach. There's C. Java looks a lot like C, right, in the structure. Objective-C is a superset of C, so you can write a C program, and it's also an Objective-C program. C++ is basically a superset of C with other classes and things. C# is like that. PHP is not. Python is not. JavaScript is very much like C. Perl is not. Visual Basic is not. But most of those are. So there's a big history there. Yeah?
What is C used? Like, could you give us an example outside of like Linux or Unix? What C is used for the used?
I could give you lots of examples. Max, what do you think?
Python, Ruby.
Yeah, it's right. Python is written in C, actually, right? I mean, a lot of these other ones are actually written in C. But no, to answer your question, anything low level is written in C these days. Even still, you know, any embedded systems, right? You know, well, probably not your microwave, maybe your microwave, but you know, things that have computers at a low level, embedded things are written in C mostly, because it's very portable and it's also low enough level that it's easy to turn it into assembly language, right? So yeah, so anything like that. Obviously, Linux is all written in C, and most of your programs are written in either C or C++ in general. Most of them are, you know, except for iOS or Mac, which are Objective-C generally, or Swift. So this is another interesting graph on this. So C is the light blue one. So it's this one here, and it goes. You can see it's kind of gone up and down over history, right? And this is history since 2002. Doesn't go past this in this particular graph, right? Java has kind of gone down, right? So I don't think we're going to teach Java as our language here, which I'm glad about. I'm not a huge fan. But look at C++, the orange one, right? It's also gone down. So, you know, I mean, if by this graph, we should actually be teaching you Objective-C, because this is, you know, whoop, this is the greenish one here. Well, this didn't even really exist in people's minds until about 2008, 2009. I mean, it was there, but it was such a small amount of people using it. And then all of a sudden, iOS, and boom, like that. So you know, anyway, C is super important because it's used a lot. This is the most important slide I'm going to show you today. Go to the web page for Comp40 and look at the material in the reference section, which tells you what all the readings are, and it tells you what the coding standards are, which in other words, how you have to write your code. For instance, normally, like with comments, like we've been kind of loose about comments. Like as long as it looks good and it doesn't go over the line length and whatever, and there's enough comments, we've been pretty lenient about your comments. They're going to have much more stringent requirements for Comp40. And you're not allowed to use the // comments at all. You're just not. You have to use the / that, and then to end a comment, you have to do that. That's just the way they want to do it. Okay? So anyway, go here, pay particular attention to the coding standards, and then just start reading it. Most of you guys are going to be in good shape. If you're taking Comp40 next semester, you're going to be fairly good, like up to speed on coding in general. If you wait until next semester, definitely go and look at a lot of this other stuff. Okay? All right. So here's a quote about C. C has the speed and efficiency of assembly language combined with the readability of assembly language. Right? It's fast. It's not. I mean, it is definitely easier to understand than assembly language, but it's not the most easy to understand language, right? You could probably argue that something like Python or Ruby or something much easier to understand in a flow sort of, you know, in a looking at it type of picture. But it's definitely fast. Okay, it's definitely fast language, and so is C++. But for what it's worth, you will find it very similar to C++, which is good. Okay, there's a whole bunch of things that are the same. You get ints, you get chars, you get floats, doubles, longs, all those things. You still get them in C, right? You get indexing using brackets. A lot of times you won't. You'll use pointer math, which we'll do in a little bit. But you can use this if you want to. There's no real benefit to using this or the other one. I guess this is easier to understand in many cases. Functions are exactly the same. you have .h, and instead of .cpp files, you have .c files. So you still have header files and you have .c files. Okay, there's no classes, so you're not going to have a class definition, but you'll still have function definitions in your header file. Okay, and then you still have while and if and for and all those things. So those are all the same. So you will find that part very, very similar. Okay. What you won't find are strings, like I mentioned before. Strings are just arrays of characters. Now, by the way, string in C++ is a class, and what do you think's under the covers? It's not a rope. It's a character array, right? So, but it hides a lot of that stuff from you. And we'll talk about some specific places you have to be very careful. No classes, no objects, no constructors or destructors. There's just no such thing in C. Okay? You have to do more for memory management. Now, that might scare you because you're like, oh my gosh, news and deletes and all that. It's more or less the same idea. Whenever you use a malloc, you need to use a free, okay, or something equivalent. But you need to do that, and it's you have to be more careful about how you actually determine how much memory you're going to ask for. Before you just say new, array of some amount. In this case, you have to say the number of bytes exactly, right? You can't just say some amount like 10 integers. You just say 10 integers times the size of an integer, which is using this command called sizeup, which is part of the compiler itself. And I'll show you how to use that. Okay? You use free. You can't pass by reference. We didn't do that much of that in C++, but in C++ you can do that. You can't do that in C. You pass lots of pointers back and forth. Okay? Everything else is passed by copying. Okay? And there's no Boolean. C++ gives you this Boolean. There's no Boolean in C. Bool is 0 means false. Anything else means true. So 7 is true. 0 is false. -4, true. Right? That's just the way it works. Okay? And so those are the big differences there. Okay? Let's talk about strings for a second. Okay. I said that strings are just these null terminated character arrays. Null is what digit? Anyone know what null is actually? Just 0, right? So you have character, 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 0, and that's your string. Okay? If you make a string of a certain size, there's actually a bug in here, I believe, in this little piece of code here. What this is doing, this is saying, make me a character array of 256. Okay, print something. We'll talk about that. A comment. fgets says, here's where I'm going to put something you're going to type in. I'm going to type it in from the terminal, and then you're going to be able to accept 256 characters, right? I believe that's a typo, because it should only be 255 characters because you have to put the null on the end as well. So I think that's a typo. Or what we call it could be a buffer overflow is what we call it. But this is how this actually works, right? 256 character array. You have to say how many characters you're going to ask for. In song search, I don't know if you've looked at the read lyrics at all, but it uses cin to get your, it says cin some string, right? Well, what's nice about that is you can have a string that's 1 billion characters long, and cin will continue reading it until it's done. You can't do that in C as easily. You have to say some number that's a maximum amount, right? So how would you read in if you only had a 256 character array, how would you read in something that might be 1,000 characters long? Any ideas? Yeah, what were you going to say? Just a bunch of pieces. Yeah, you'd have to say, just give me the first 256. If you're not done yet, give me the next 256. If you're not done yet, and so on. And you have to manage all that. So there's more management than before. Okay? More management than before. And you have to worry about buffer overflows, right? You do a little bit in C++, but in C in particular, where's my eraser? In C, you have to be really careful that you don't say something like, for this up here, string 256. If I said string 280 equals the character A, is the compiler going to complain about that? No. The answer is the compiler doesn't care. The compiler says, oh, you want to do the character at 280? You must know what you're talking about. OK, so it's going to let you do that. And this would actually go somewhere off in memory past your 256 character array and put an A there. And that might be bad, because that might be trampling on your stack or some other piece of data. Right? So you have to be careful. That's called a buffer overflow. And it's the reason hackers exist. Right? Buffer overflows happen in all sorts of code, and they're hard to check for. And I did one right here, right? If I ask for 256 characters and you give me 256, that 257th character is going to be a null, and it might be smashing some other data, right? So that's you have to be careful with that. So C will give you lots of chances to segfault because of things like this. Okay, you just have to be careful with it. All right.
What do you mean by that's why hackers would use? Like, is it easier to
Well,
things that have problems because of?
yeah. So you've got a bug in your program, and the bug allows somebody to put some piece of memory into your program, or into your memory system, to put some data into your memory system that you don't know about. So it can either crash, or most of the time it crashes your program. But hackers are really good, because they can look at something and then go, oh, if I'm really sneaky about it, and I call this function a lot of times or whatever, maybe I can have the data go there, and then if I put some other data, I can run my own code or something, right? So you can be really sneaky about that. If you happen to change the return location for your function, and you change to some other function that you created, well, then all of a sudden you're running your own code instead of the one that the program designer wanted you to, right? So it's all hacking exists in a lot of cases because of buffer overflows. Because you're letting somebody else touch a piece of memory that you don't know about. So it's tricky. OK. This is hard to see from the back, I know. These are a bunch of functions you can do on character arrays, right? It's in the, I forget what library, the string.h library. And it tells you that you can do things like string compare two strings. Now, remember, it's a pretty low-level language. If you're comparing two strings, it will compare them alphabetically, and then it will report one of three things to you. It will either give you a negative number if the first string is less than the other one, comes before it in the alphabet. It will give you 0 if they happen to be the same, like they have the same characters in them. And it will give you a positive number if it's greater, if the string that you pass in first is greater than the other one. Now, what does that mean? It doesn't tell you what greater than, what number. It could return 5 to you, or it could return 27. If it's 27, it just means they're different. You can't use that 27 for any other reason, right? This is just all they give you, right? Just a positive, positive, negative, or 0. And part of that is because they can do it fast. That's really what they can do. You can also concatenate strings, like put two together. You have to be really careful. This destination pointer is where you need to put the result. If you have a destination and you've only got 256 characters for it, and you try to concatenate two strings that are both 300 characters or 200 characters, well, what happens? Buffer overflow, right? Because you've not given it enough space. So another place you can have buffer overflow. You have to be really careful, right? You can copy strings, you can do string length and everything, but lots of little functions, but you'll get used to those. Okay? All right, what else? Structs. Structs do exist in C. They are a little bit different in that they're not classes under the covers. They are very simple. Okay, structs, you have to do something. When you have a struct, if you declare it like this, you then, every time you want to use it, you have to say struct and then the name of your struct and then do what you want. Or you can actually create a new type yourself using this type def, do the same sort of thing, and then you call it that name, and then you just use this name as you would in C++. It's a little bit different. So don't be surprised when your structs look a little different in C. OK? Yeah, question?
When you do a class, do you in C++, are you basically doing a type test? Or
In C++, it's much more in-depth, because classes are much beefier objects. They're actually objects, and they can have functions in them, and they can have all these other things that C structs can't have in them, right? C structs can have pointers and can have types, regular, ints or floats or chars. That's really it, right? They can have other structs and things, but it's nested, but that's really it. Yeah. Okay, you'll get into details about this when you start. Just don't be like confused about that. Okay? There are some things that are the same that we probably didn't talk about in here, right? There's these weird things called void pointers, which means that you might get a value, a pointer back from a function, and that pointer can point to anything, right? It doesn't say it has to point to an integer array or a character array. It can point to anything. You then have to cast it using the parentheses, and we've done some of that before, right? Where you put like parentheses int, and it says, okay, that means that what's coming next, I'm going to make it into an int. Okay, well, the compiler is allowed to do that. But you have to do that with these void pointers. Okay, I'll show you the example in a second. Pointer arithmetic, we use that more than bracket notation in some cases, just because it's tradition, really. I mean, it's not. You could turn a lot of it into bracket notation, but a lot of times you'll see pointer arithmetic. Again, can't use a double slash. You can use it, but you have to. For comp40, you have to use these other kind of slashes. Okay. All right. So when you want to get a certain amount of memory for your program, you use this thing called malloc. Okay, and malloc is interesting because you have to tell it how many bytes you want. Now, what does that mean? What's a byte? You better remember. Yeah, Alice. It's 8 bits. Okay, so with 8 bits, you get 2 to the 8th number of things you can represent, which is 256. So a byte is a number that goes from 0 to 256, or well, 255. Okay, that's 1 byte. And it turns out that integers, we used to have 1 byte integers, okay, but these days we have integers that if you do the following, if you say size of int, the compiler will return the number. In our case, generally will return 4. Okay, it's based on the fact that we're using, well, it's kind of based on the fact that we used to use 32-bit architecture, right? Which is 4 bytes worth, because 2 to the 8th is 8 bits is 1 byte. How many bytes is 4? Or how many bits is 4 bytes? 32. So the fact is that they used to just make ints equal to the 32-bit architecture, part of your what your computer's like kind of basic value is for addressing. But now it's now we use 64-bit, but they more or less left these the same. Okay. But anyway, it's 4. So that means you have 4 bytes. So if I want a character array of 3 integers, how many bytes do I need? If each integer is 4 bytes, and I need 3 of them, right? How many total bytes do I need? 12, right? Yeah, I need 12. This will help you figure that out, this size of. I'll show you how to use that, maybe on the next slide. Whoops. Yeah, here we go. If I want 10 ints from the heap, I create an integer pointer. In other words, if I want an array of 10 integers. And then I say, look, int pointer equals, I have to cast this to an int pointer because malloc returns one of these weird void pointers. And then I say size of int, which is 4, times the number that I want, which is 10, and this will give me the 40 bytes. Just like new would in C++, it will say, here's 40 bytes contiguously. You get to use those. Okay? If you happen to run out of memory, you end up with null. Question?
So for like a character, would you say like size of character times 10?
Yeah, if it was a character, it'd be size of character. And generally, characters are 1 byte. As far as I know. I think they are, yeah. Generally, characters only take 1 byte. Yeah. So yeah, you do exactly the same. And the size of also works for structs, by the way. So if you have a big struct, you don't have to count how many bytes it has. Size of will work on it. The compiler can count. Computers are good at counting. Right? If you happen to run out of memory, you get null. That probably won't happen too often. Maybe for song search, but I doubt it. Okay. And then how do you return the memory? You use free. Yes?
Does new return null?
New also returns null. Yeah. We checked it once for maybe a lab. I think we checked it in one lab. Yeah. Behind the scenes, the operating system keeps track of how much you asked for when you malloced int pointer, so it knows how much to take back at the end. Okay. All right. So let's go into a little more detail. Now I'm going to have you put your thinking caps on for this. Here's a program. Okay, I will tell you a little bit about this program. This is exactly what we did up on the previous slide. This, just a loop. There was some pointer arithmetic in here. And then we're going to print out something. And printf, we'll talk about what that means in a minute. But all that's saying is print what this tells you in decimal form, okay, in like integer form. So here's what I want you to do. Take a look at this program and tell me what this is going to print out. Okay? Look at it for a minute. Talk to your neighbor. I'll start drawing it on the board and see what that prints out. Okay? Try to figure it out. Can you guys read it in the back? Okay, good. Think a little bigger for you.
Does in the printf,
Mm-hmm.
times that means it would be that times itself?
Be that times 2
Yes.
plus that. And this means dereference that pointer, because that's now a pointer.
Okay.
Yeah, Graham?
Is it more common practice to declare the list iterator outside of the?
Yeah, in standard C, you have to declare the variables outside of 4. I think in the one you're going to use, you can do it inside. But normally we do it outside. It's just a little easier. Yeah, Max?
C99 would be C90 for some part of the class.
Oh, does it? Yeah, you may not be able to do that for some of the class because of the compiler you're using. But in general, yeah, you do it outside. Yeah. I like doing it inside because it keeps your scoping better. Like you don't have to worry about I being available later, but some people don't like it at all. OK. Jade, do you guys know what it's going to print? OK, let's talk about it. That sounds good. I'll let you explain why you think that in a second. OK. So did I get this right? Like you're going to create, with the malloc statement, you're going to get 10 integers, of whatever size this is. These happen to be each 4 boxes, 4 bytes each. OK, 0 through 9. OK, so what is this first? Let's walk through this first loop like to begin with. OK, Jade, I'll let you guys talk about the second loop. Somebody walk me through the first loop. What's it doing? Somebody over in this corner. Yeah, Sophia, what do you think? You raised your hand.
I did not raise my hand.
You kind of did. What's it? So we're gonna loop through it how many times? 10. Okay. And then what? This is not a trick question. And then what's going to happen here? What's this going to do?
Cecily, what would you do?
Sam?
It's going to assign a value to each element.
OK, so this says, look, dereference whatever this value is in memory. Int pointer points to here. So this is int pointer. This is int pointer plus 1. This is int pointer plus 2. What's nice is the compiler knows how much to jump each time. It will put you in the next box appropriately. OK, so what do we put in box 0 then? 0. And what goes in box 1? Why is it 10? Because it's whatever the I is times 10. So then it's 20, 30, 40, 50, 60, 70, 80, 90. OK, everybody got that so far, right? OK, Jade, over to you. What happens in the second one, the second loop? OK, it goes 5 times. OK, and then what's the first thing that gets printed out? What's this all about? What's I during the first iteration? 0. So you're going to print out whatever's at int pointer, and what is that? 0. Okay. And then what is it? And then I becomes 1, and what gets printed out? Well, let's see. I is now going to be equal to 1. 1 times 2 is 2, and it's going to be whatever int pointer is plus 2 spots. 1, 2. What gets printed out? And then what gets printed out? 40, and then 60, and then 80, and then anything else? We're done. OK. What's that? You were right. All right. Now, that's using, you could have used bracket notation for all of this, but you're going to have to get used to seeing it in this notation because you'll see that fairly often. OK? All right. Now, the other question is, what the heck is this little statement printf? And what is all this baloney in here? Well, let's go into printf land for a second. OK? There. Printf, OK, is just, it's like equivalent to cout, except it has lots of formatting that is associated with it. Here's what you do. It's easy. Printf, and then you have a string here with some formats in it. Percent means the next thing is going to be some formatting character. In this case, D stands for decimal number, like an int, right? And whatever is the after the comma here, the first percent whatever gets whatever that value is. And you can keep putting comma, comma, comma as many as you have for percents in here. So this is going to say this is I. Print out a number that is I, because that gets replaced in there. In this case, it's 22. So what happens is you get 22 out of it. OK, that's how printf works. OK, if I had been 30, it would have gone this is I colon percent D says, well, the first thing after here is 30. Therefore, I'm going to print 30. Yeah, your question.
Matter that it's percent D or could it be a percent anything? It doesn't go by order.
Well, whatever this D, on the next page I'm going to show you is all the different formatting strings, but this says it's going to do a decimal. Sorry, an int value. Yeah.
So you do like this is I, like percent D, comma, and then another percent D, and then have like I, comma, X.
Yes, exactly. That's exactly. So on the next, I'll show you exactly that. Yep. So you basically can string these things along. Well, before I show you that, here's all the a bunch of different formattings. Not even all of them, right? You can print out hexadecimal numbers. You can print out floating point numbers. You can print out scientific notation. You can print out, let's see, characters or strings. It will print a string for you as well. Okay, and all those are in the all those are inside the inside that string. Or inside that printf format string. Okay, I've never used this one, the %n, before. Nothing gets printed, but then it like stores the value of how much has been printed so far. It's pretty neat. Is it useful? I haven't used it before, but anyway, it's lots of different ways. You can print out pointer addresses. Okay, so you can look at more examples of this. But here's some examples that I'll show you. And this is exactly what you were asking about. What happens here? So look at this. This will print out characters. %C, and then a new line, right? It prints out lowercase a, because that's a character, and then it prints out whatever the character equivalent of ASCII 65 is. Anyone know what that happens to be? Uppercase A, right? So when you do that, it prints out characters colon A. That's how it works. Okay, you can also print decimals in a couple different forms. You can print out fancy blanks. If you do % a number and then D, it will print 10 blanks and then the number. Right? Actually, that's not true. I think it will print the number of blanks equivalent to make the whole amount 10. I think that's what it does. Then you can print leading zeros if you want. You can print all sorts of radixes. In other words, you can print octal numbers or hexadecimal numbers, or you can't print binary numbers for some reason, but you can print decimal numbers and all that. Like that, okay, if you want to print them in various formats. If you see a 0x64, the 0x says the next thing is hexadecimal, base 16. We'll get into that in a minute. Okay. Then you can print floating point numbers in all sorts of different formats. You can tell it how many decimals to print, all that. You can print weird width tricks where you say, like, I want this whole thing to be 5 characters wide, and it will do that for you. Yeah.
Why is 0, 1, 0, D? Why does that correspond to 6 zeros?
Sorry, which one?
Proceeding with zeros.
Proceeding with zeros. So 010D. I'm not. You know what? I'm not exactly sure. But I think when the 0 says it's going to be proceeding with how many zeros? 10 zeros or something like that.
I think it's
Or is it?
like the whole thing.
It might be the whole thing is maybe so the whole thing is 10 total. But the 0 says, oh, that's what format is, and then it needs another argument. So that's what the 10 is. Yeah.
So if that's true, why for the second thing, it clearly printed one blank, or is that, oh, the one blank is from,
This one?
is
This
actual
one.
space? Yeah.
Yeah, there's an actual
Okay.
space. Yeah. Yeah, there's an actual space.
So what's the one for that one then?
Which one? This, oh, L? LD means long. Yeah. So it's a prints that happens to be, I define it as a long number, which is 64 bits instead of 32 bits in this case. OK, and then you can also print strings, of course. So you just print the %s and then a string, and it will do the string. OK? And these are character strings again. OK? Sometimes you might do %s and then give it some value that's not a string, and it'll print all sorts of garbage until it gets to a null. Because it'll just keep going through memory until it finds a null, or segfaults. But that happens a lot. It's not a string. It's a character array. Yeah. I mean, I'm calling it a string, but they're kind of interchangeable in C. I mean, when you talk about a string in C, you're talking about a character array. So, yeah. OK, so that's that.
What is the reason for F, like printf and F gets? Just like why did that?
Why F? Yeah, go ahead. Here, no? No. Oh, OK.
Yeah, no, I did have a question. I see you're calling on me.
Oh, OK, hold on. I thought you were going to answer this question. Hang on a sec. So what's the reason for F? I believe it stands for like file. So you can do that, or maybe print. Well, in this case, it's print format. So I think the F is format. Is that what you're going to?
Yeah, I know the things like F gets and F open and whatever it's file.
Yeah, for other ones like F gets, it's like file gets sort of thing. So it's they had to use it for different things. Yeah.
So like for this character array versus like the string kind of thing,
Yeah.
could you say like character array 10 equals like 10 characters that are in parentheses? Like a string?
You could. No, yeah. Well, so that's a good question. How do you do that? Let's say you wanted to do a character string that was hello, right? You would have to say like character and then H, let's say 6 equals hello, right? And what that tells you is put my string hello into these 6 characters here. And why did I do 6 when hello only has 5 letters? Because you need the null, right? So you have to remember that. Okay? Yeah, so you can do that. OK, let's move on a bit. OK, so we know what this prints out, 0 to 20, 40, 60, 80. Good job, everybody. Okay. We talked about the pointer arithmetic, right? We talked about this idea that an integer is 4 bytes long. OK. And it will jump by an integer each time. And the compiler figures all that out for you. So no worries about that. Okay. Let's go into a little more detail. Now, I can pull this up if you want. If you want to go look at some of the, look at the actual program, I put a little file online. And it will give, this is hard to read. But you can go and you can run this. If you have it in a debugger, you can go to like halfway through the program, right? Stop it, and then a good debugger will allow you to look actually at the memory of that pointer there. And you will get used to seeing things like this, right? This is another one where your eyes could bleed a little if you don't watch out. But you'll get used to seeing this. Notice in this one, I'm running the program right now, and it says, you can't read it from back there, but 0, 0, 0, 0, 0, 0A, 0, 0, 0, 0, 0, 0, 14, 0, 0, 0, 0, 0, 1E. OK, so you get the idea? It's got a bunch of zeros in there and then some things. Well, this is what I've made it bigger here. OK, this memory diagram of what's in memory there, we have to kind of figure out what it means, because you're going to have to do that when you get into Comp 40. You're going to have to say, what does all this mean here? Well, first of all, this is an address. OK, it's like literally an address in memory that the pointer points to. So if you were to say, what is the pointer value, that's the pointer value. OK, 100203A10, hexadecimal number. OK, And then it has this like craziness here, right? It's like 0, 0, 0, 0, 0A, 0, 0, 0, 14, 0, 0, 0, blah, 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 blah. All right. So we have to like figure out what these numbers really mean. Can anyone tell me why there might be all those zeros in there? Any ideas? What do you think, Alice?
Maybe it's so. I mean, at least the ones to the left might be due to. It might be like few heads. It might be just like higher. It's like not the tens place.
Yeah, the higher like place in the number. So how long did we say? How many bytes did we say our ints were? 4 bytes. Guess what? 1 byte, 2 bytes, 3 bytes, 4 bytes. That is one integer. That's another integer. That's another integer. Okay? Now it looks funny, and we'll talk about why that looks funny in a second. But let's delve a little bit into hexadecimal land, okay? First of all, I said that the pointer is a hexadecimal number, base 16, right? And we use hexadecimal a lot mainly because each hexadecimal digit is 4 bits long. Why 4 bits? Well, hexadecimal is 16 like digits, right? First of all, why do we count in decimal? Anybody know? Like, why do we care about decimal? Yeah. Yeah, but why 10? Yeah, because we have 10 fingers, right? Cave people a long time ago were like, oh, I better learn how to count, right? And where's the first thing they did? They went, oh, look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, 10 fingers, we're going to count in base 10, right? Took them a while to figure out 0 also, by the way. But anyway, 0 through 9 are the 10 digits. Why 10 digits? Because we had 10 fingers. It's, what?
What if you had to code in Roman numerals?
You would fit a code in Roman numerals. Roman numerals are a bad system for that anyway. So unfortunately, as far as I'm concerned, I happen to be a firm believer that if we had 12 fingers, it would have been better because base 12 is actually a better base than base 10. 16 fingers would have been great because then we would already be in hex and you wouldn't have to know, that stuff would come like naturally. Yeah.
Why 12 over 16?
12 over 10 because there's more things that go into 12 equally. 2, 4, 6, 2, 3, 4, and 6 all go into 12 versus just 2 and 5 go into 10. It's terrible. You can do a third without a decimal place. That's nice. Anyway, different story. You can all join me in the dodeca whatever club or whatever. Anyway, so the nice thing is hexadecimal, 4 bits each, half a byte each. So guess what? 2 hex digits is 1 byte. 1 byte, 2 bytes, 3 bytes, 4 bytes. It's much easier than doing it in decimal. So that's one of the reasons we do it. We look at it this way. Okay? All right, let's get into some details about hex. Because we don't have 16 fingers, because we have 10 fingers, we only needed 10 digits, 0 through 9. If we all of a sudden are trying to count in base 16, we need more digits, right? Well, some smarty pants said, let's start the new digits at A, right? So we go 0 through 9, that's the first 10, and then you start A, B, C, D, E, F, and that gives you all the way up to 15, which is enough to make 16 digits. Okay, so that's why you have 16 digits here, and that's why you have the extra A, B, C, D, E, F. All right? Well, it turns out it's pretty easy to do conversions between these things. It takes me a little time to remember every time because I haven't done it in a while, but it's easy to do once you remember. To convert from decimal into hexadecimal, divide by 16 and keep taking the remainder until you have no more numbers to divide by, like this. The number 2,913 in decimal. Divide it by 16. That gives you 182 with a remainder of 1. That means that 1 is the least significant digit in our hexadecimal number. Well, we got 182, divide 182 by 16. You end up with 11 with a remainder of 6. 6 is the next hexadecimal digit. 11 divided by 16 is 0 because there's nobody left. 11 is your remainder. What's the hexadecimal digit for 11? B. So that's our next hexadecimal digit. And then finally, we don't have any numbers left because we got to 0, so we're done. So the number is B61 in hexadecimal. Okay? The nice thing about hexadecimal is that it compresses numbers pretty efficiently. You go from 4 to 3 in this case. Works even better for bigger numbers. Okay, and you can do that. All right, another example, same exact example, except now we're going to do a bigger number. 43,981 divided by 16 gives you 2,748, remainder 13. 13 is the least significant digit. 13 happens to be D. Keep doing the same math, and you get DCBA. So the answer is 43,981 in decimal is A, B, C, D in hexadecimal. Okay? What's kind of neat is you can actually spell out real words with hexadecimal. So that's kind of neat. We'll talk about that in a minute. Going the other way is easy. Because it's base 16, you take each digit, you multiply it by its equivalent power of 16 in whatever place it happens to be in, the ones place or the 16s place or the 256th place, right? You multiply by that, and then you get the number back. So D times 16 to the 0 is just 13, which is D, times 1, which gives you 13. C, which is 12, times 16 gives you 192. Add all these up, and you end up back at 43,981. Okay, it's pretty easy to do once you do a little bit of arithmetic on this. Okay. All right, so back to where we were. Now, I already said that those 4 bytes gives you 1 integer. Okay, so in our array up here, because this is what our array is in memory, the first integer is 0, and that's these 4 bytes. Okay. What's the next integer? What's that one? What is it supposed to be in our array? 10. Do you remember what the character for 10 was? A. Look, is there an A up there? There is. This number in hexadecimal, 10 in hexadecimal, happens to be 0, 0, 0, 0, 0, 0, 0, A. That's 10. Anybody want to guess what 20 is? 0, 0, 0, 0, 0, 0, 1, 4. Right? It's this one. Okay? Now, what's the problem with this? It's backwards. It's kind of backwards. It's really odd. Okay? What's happening here, okay, is the way that the people who designed your PC, they had to make a decision. And they had to say, how are we going to represent numbers in memory? This location in memory is less than this location in memory. Okay? This number comes before this number in memory. And what they said was, in memory, we are going to store our numbers in what we call little endian form. In other words, the little end of the number, like it sounds funny, but it's the little end of the number is going to come earliest in memory. Of these, this number here, oops, right? If we break it into 4 ones, the littlest part is this one. The next littlest is this one. The next littlest is this one, and the biggest piece is this one. And so what they do is they represent this one, this one, this one, this one backwards in memory. Now you'd say to yourself, wait a minute, why don't they just, if they're going to do that, why don't they just exchange everything? Why do it by these bytes? Like, why not make it, let's see, why not make it like, well, I guess, yeah. Why not, instead of making it 0, 0, A, why not make it A 0, 0, 0, 0, 0, 0, 0? Right? That's a long answer to that question. But the answer is really that the byte is kind of like the atom to a computer. It's like the lowest amount you can represent as an address. You can't represent a number that's lower than a byte in memory. Okay? You can go in there and like the electrons are the bits in that byte, but the atom itself, like the byte, is the atom itself. Is that a good analogy? That makes sense? I mean, basically it's saying, look, if you're going to reverse this, you can only reverse it on the byte level. You can't reverse it anymore. So they do that. They reverse it this way, and they say 14,000 is the, what we call little endian representation of the number. Yes? Yeah, it was just a design decision. They said, hey, let's just make it so that memory goes, as you go up in memory, you start with the least significant bit, or least significant byte, and go from there. Yeah, Graham?
Why are there 3 integers being stored in one address? Am I reading that right?
Not quite. Yeah, good question. Why are 3 being, so this address is blah, 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 A10. That's this one. This one is A11. This is A12, this is A13, A14, A15, A16, 7, 8, 9, A, B, and then hopefully this one will be A1C, which is this one. So it's each individual one is one more place in memory. Okay? Yeah. So that's how it's represented. What's nice is when you do I plus 1 or int pointer plus 1, it starts here and then knows that the next one starts here, and it knows that the next one starts here, etc. Now, to answer your question, why did they make this decision about little endian? It was just a design decision. They had to do it some way, and that's the way they did it. Other architectures do it the other way, where they do big endian first. Right? Networks do big endian. So if you send a number over a network, you're generally going to send the highest order byte first, and then you're going to receive the highest order byte first, which means you have to be really careful. Lots of people have written programs that deal with the network and try to dump data, raw data over the network and come out with garbage because they forget this whole little to big endian switch. Yeah, Elena.
Does it know to go up by 4 because I was an integer?
Exactly. It knows to go up by 4 because I is an integer, and the compiler says, oh, integers are 4 bytes, therefore we jump by 4. Exactly right. Whew. Yeah?
Does the fact that there happens to be like 3 addresses in a row up there actually mean anything in the computer, or is that just the representation?
No, it's just the way it was fit on the screen, really. Like when they give it to you, that's the way it fits on the screen. Yeah. So yeah, so the fact that there's 3 here doesn't really mean anything. Yeah. Whew. OK. So it's a lot of stuff. This little endian stuff is confusing at first. And it's weird. I mean, just because it's, again, it's not 410, it's 14, because that's the byte. The byte is as small an amount as you're going to get by itself. It's the atom. Okay? All right. So that's what we have there. If we add a couple more integers in here. So let's do this. Dereference int pointer plus 8 becomes 0x beef. Because as I said, you can write like real words here, right? Microsoft is kind of famous for putting dead beef in their code some places, like where they have lots of empty space. And they do that so that it's easier to debug. Because so when a programmer's, like it's like 4 in the morning, the program's been up all night, and he's looking at his code, and he notices a spot that should be empty, and it says, or it should be empty, and it says a bunch of garbage, and it doesn't say dead beef, he knows something was wrong. It's like a debugging tool. So they did that. There's other ones too. Yeah?
The hash function file that you gave us
Yeah.
has dead
Does it? The hash function file has dead beef in it? There you go. It's a pretty typical one. Yep. Bad beef's another one. Dead beef. I'm sure you can come up with other letters that are feed, all that stuff. So anyway, so if we put beef, 0x beef in here, notice if we're going to write this out, if you wrote this little endian, it would be EFBE0000. And look, it goes into memory like this, EFBE0000. Okay? Same thing for this one, ABCDEF01. The lowest order bit is 01. That's going to come first in memory. Then EF, then CD, then AB. 01, EF, CD, AB. OK? So you're going to have to get used to that, seeing those. Okay? It's not that hard. It's just all of a sudden it's, oh, I got to think about it. Okay? All right. Yeah, I know. You have to think. OK? Yeah?
What's it doing for certain actions? Because like so we're storing an int, but we write something that's not an
It is an int. 0xBEEF is an int. It's a hexadecimal integer. So it is an integer,
so it'll just store exactly that.
and it stores exactly that. Because that is an integer in hexadecimal. Because E's and B's and F's are hexadecimal digits. And you tell it it's a hexadecimal by putting the 0x in front of it. Yeah. Yep. So it's not a string there. It's now actually a number. Okay. All right. So we've talked about hexadecimal. Now we do use binary. Now you're going to have to do a lot of binary. You have to do these like weird bit packing things, and it's kind of fun actually to write these programs. But you need to deal with the actual, it's like dealing with the electrons inside the atom, right? It's like another level of kind of intensity in this case. And you have to do these bitwise calculations. It's very similar to the truth tables we talked about for the binary decision diagrams, right? It's all like truth table stuff on the 1, 0 level. But we do need to like figure out how to go to binary. But guess what? It's just another base. Converting to binary is easy. Just divide by 2's, right? Just keep dividing by 2. If you divide by 2, what are the only possibilities for the remainder? 0 and 1, right? And there's your binary digits. So 23 divided by 2 gives you 11, remainder 1. That's the least significant digit. It's exactly like hexadecimal. And then 5, remainder 1, 1, 1, 1, 0, 1. And so the answer is 1, 0, 1, 1, 1 is your binary number. What's the problem with binary numbers? They're huge, right? 23 turned into 1, 0, 1, 1, 1. Not a very efficient way of representing things. So what do we do? And by the way, going backwards is the same. You have to add powers of 2. What do? Right? We don't want to represent 5 million with a giant binary. Talk about your eyes bleeding. Like if you have to look at this all day, you're going to be blind really fast, right? Because you will, you'll stare at it and you don't. All the ones and zeros just kind of become a jumble. It's not fun to calculate with large numbers in binary. So what we do is we say, wait a minute. We learned this hexadecimal thing where each hex digit is 4 bits, which means that you can compress binary numbers into hex numbers very quickly and very easily by just remembering that for 4 of them, you get a hex digit out of it. 0, 1, 0, 0 in hex is 4. 1, 1, 0, 0 is C. So this huge long binary number becomes the hexadecimal number 4C, 4B, 40, which is not easy to remember necessarily, but a lot easier to write down than this giant number. And it's easy to go back and forth, right? You look at that C and you say, OK, that's going to be 1, 1, 0, 0 in binary. How do you know that? Well, you've got your little table that tells you. OK, so it's kind of neat. You get the benefits of binary in a form that's easy to read and easy to store. OK, that's why we use binary and hexadecimal. Yeah.
So if we're trying to compress like a number further or compress something further and send it between machines,
Yeah.
could it be useful to use just higher powers? Or like what's the problem?
Well, here's the problem with that. Signals are generally 1s or 0s. You have 2 levels in a signal. You have either on or off, basically, right? And when there are machines that there are machines that allow you to do more levels than that, right? If you're transmitting anything on amplitude mod, AM radio, for instance, can use various levels based on thing. So you can get more levels out of it, but you're generally going to be limited in the end to back to 1s and 0s. So the computer is going to be very happy with 1s and 0s because electronically speaking, you get an on or an off state, and that's it. It's a transistor basically. It's on or off. So you get that. So under the covers, everything's binary. But we represent it in hex. It's easier to represent and efficient to represent. That's it. OK. All right. So I believe that's that for Comp 40. Here's the bottom line on Comp 40. Like I said, you're going to do fine in it. OK. It's going to be, for those of you who take it, I think you'll get out the other end and say, boy, that was a cool class. OK, I'm glad I did it. While you're in the middle of it, you'll be like, what have I done? Right? What have I done to myself? But I think you will really enjoy it. The assignments are very similar from year to year, so you will have almost the same experience that the last class that went through had, right? The teacher doesn't really make as much of a difference in that class because it's like it's the class itself and the design that's very good. Don't let it scare you. You're always going to have a partner to work with, so it's not except on the mid-year and the final. But otherwise, you'll be able to work on all these projects. If you're not a coffee drinker, you might want to start, right? But and have like a travel pillow you can bring to Halligan. But you guys will do great. You guys will do great. Any last minute questions? Okay, we'll see you guys Monday.